taking part in some research and academic interaction. So, on behalf of the institute, I welcome all of you to this SPARC program. And as you can see, I looked into the theme of the SPARC program, and this theme is very important, but at the same time very broad-based. So, what I would like to do is to give a broad-based overview on how technology, typically diagnostic technology, is creating a kind of impact which is just the beginning, but the real impact on the grassroots level. And I will also talk about the challenges, opportunities, etc. Not that all problems are solved, but in fact only a few problems are only partially solved. So if we look into this entire aspect of going for innovations in diagnostic technologies, we have to get a broad perspective. And people like us who have been working in the field from a time when many of the technologies were not that advanced, we have a bit of overview, and which is very practical overview, because students who have more recently started working on these, they will not know that all these things started at a time when many of the technological things which are currently so obvious were significantly challenging in that era. So if we just give an example of how the entire approach of giving healthcare to the last mile became what you say as democratized or decentralized, it is primarily through telemedicine. And telemedicine was a terminology which became common maybe in India 15-20 years back, not earlier than that, possibly 15-20 years back. So around that time, there was a significant effort, and that effort has now translated into developing so many sub-centers, digital health units, and these are all connected by common national missions like Ayushman Bharat and several other such types of schemes. Now, if we see what these centers were when they were perceived, and still now the same digital backbone is maintained, but technology has advanced very much. So, what has been the essential foundation? Say a small room in a village, it could be a brick and mortar room, it could also be a bicycle, it could also be a motorized two-wheeler, and in an extreme case, it could be also a launch in Sundarbans. So it could be a fixed or a mobile unit. That unit has some individual or a collection of individuals whom we collectively call as frontline health workers. And frontline health worker is a very generic terminology. It could be someone who is not having in a literal sense any formal education to do such activities, or formal education to the level of a certification program, which is the certificate for allied skilled health workers. For a long period of time, we have been working in such a system in collaboration with Dr. Chakroborty, who represents the Foundation for Innovations in Health, and he himself FRCS doctor, but he runs this not-for-profit foundation where we have the trained frontline health workers. But in the last 1 year, we have established such a skill development program within IIT Kharagpur. So now IIT Kharagpur itself gives the certificates under the ministry's banner for the skill development. So the objective is to have human resources who are not, of course, doctors, not nurses, but at least they have some competency to do certain activities. What are those activities? So let us say a patient comes, and when the patient comes, patient interfaces with this frontline health worker, typically a minimally trained boy or girl. So this frontline health worker will record the different data that come from the patient. Some are like identity data, which may come from ID card, or even the patient can tell a bit of family history, medical history. Sometimes travel history is also connected with medical history, and then symptoms, also the frontline health worker can record some basic body vitals like blood pressure, pulse, oxygen saturation. These are basic things. Someone has fever, then temperature, height, weight. These are basic things anywhere in a primary setup one can do. So these things can be input. Also nowadays, because smartphone is very readily available, so if someone has a skin rash or someone has a yellowish eye, that photo directly can be taken and uploaded in the system. So that much is this person is authorized to do. This person may be very experienced, but this person is not in a position to take any kind of decision. Just put these things into the system, whatever records are available, or whatever images can be taken. Now we, because of AI advent, it may be possible to actually take a recording from the patient in some local language, which may not be understandable so easily, and translate it to one of the acceptable languages with which the expert can work. So many of the opportunities are coming. But when this initial recording of the data is over, then what this frontline health worker does? The frontline health worker communicates this to the doctor. There are two scenarios. One is a physical doctor present. This is not the common scenario or the design scenario. This happens sometimes, and typically, I go to many such places and camps, and when I see that we as a visiting team go, they are in a ceremonious manner, they are organizing things. So physical doctor is there, but regularly you will not get physical doctor because of the challenge in getting doctors in those places. Even if you get, you will not get specialist doctors. You get maybe one or two who are just voluntarily doing something. Then the obvious option is to connect the patient to a remote doctor. The remote doctor is sitting somewhere, and as I was telling you that 15-20 years back, connecting the remote doctor with the patient and the frontline health worker who are sitting together, and it is important to communicate when both of them are there, because patient may not be in a position to even communicate for whatever reasons, or communicate in a meaningful way. Patient is telling vague things, and that has to be converted to something which is more specific. So that in that era was something for which people required significant bandwidth in the internet network, which was not existing. But thanks to this internet network revolution, communication revolution, which has come up over the past around 1 decade, that you have started with 3G, 4G, 5G, and it is going on. All the remote places are connected very, very well. I mean, not that everywhere the internet connection is perfect, but much, much better as it was in comparison to what it was several years back. So that connectivity is now not a problem. The doctor interfacing with the patient in real time is now absolutely easy. If nothing is available, WhatsApp video call is quite common, and then people can do that. Previously, specialized software platforms were required. Now this is something with which they can always do that. But the challenge comes that what the doctor will do at that. Even if you are going to a physical doctor, in the first visit, the physical doctor, unless it is a very, very straightforward decision case, physical doctor will have a bit of, I would not say trial and error, but sometimes watch and go. So for example, someone has come with a fever. Now, in rare cases, just by the fever alone, you can have a decisive opinion that this fever is due to this. So maybe 1 or 2 or 3 days with paracetamol small and wait, and then things are not improving certain things. So, not just for fever, for most of the things, the first line is some essential medication. And this essential first line medication is now very commonly available in generic medicine shops. The challenge becomes when the doctor, in addition to this, also has to advise diagnostic tests. Now, the diagnostic test is something which, even in the essential preliminary form, it requires some resources. And we have to be very, very clear, typically in the modern era when everyone says that with AI you can do everything, unfortunately diagnostic test and AI, they can come together and actually make one strengthen the other. But AI without diagnostic test is a joke. It is not anything which is clinically supported. So one has to have at least the facility of the essential diagnostic test, and that will require very few common things. One is that either some fluid is collected from the patient, blood, urine, saliva, whatever, swab. So that with that, the test that has to be done, that sample has to be transmitted to one of the labs, whatever is the nearest, but that also is not that near. And during that movement there can be sample degradation. And even if nothing else, the time delay can be very, very critical for taking the decision. Cost factor is also there. The other one is even more severe in terms of the challenge to the patient. The patient has to be taken to the center. Let us say it's a medical imaging which is required. Then you cannot image without the patient. So you have to take the patient to the center. The road condition can be bad. Even if everything is alright, but patient doesn't want to go simply because he or she will lose a daily wage. And on the top of that, if it is very expensive test, patient many times says, no, we don't have. So at the end, large number of people, they are not being able to be sort of interviewed just because of these challenges. So now when these challenges are there, people can readily answer that, okay, we have point of care diagnostics. So instead of patient going to the clinic or center, we can have a small setup made accessible to the patient, either at the doorstep of the patient or maybe a very nearby place. Concept-wise very good, and large number of publications therefore we can see in this domain of point of care diagnostics. Because this has actually democratized the way in which one can in principle do diagnostic tests. But this is where there is a significant gap, that what is the ideality in point of care diagnostics? That ideality is confined only in that paper of nature biomedical engineering or biosensors, bioelectronics, whatever. On the ground, if you bring it, it is F grade. So what is happening, because of which it can give glamorous publications, but in real test it fails. This is what academicians don't want to answer, because it is not related to academic progress. For students also it doesn't matter, you publish papers, you get a good postdoc and all those things, you move forward. For faculty also it is from one promotion to another, big awards, so who cares whether this works or not. But if nobody cares, then this will all become like a showpiece, and it doesn't actually work in practice. So how we can make it better to at least improve to work in practice in some way, and this is where we must give attention. Otherwise, research in diagnostic technology is not like research in integral or differential calculus. One is to understand this. If it doesn't serve the purpose, then it is no research. So now what we have to see, and this I will sort of share with you some of my experiences instead of getting into individual technology details that takes a huge long time. I want to just give you the overall perspective which is important for any such SPARC program. So every time when we develop technologies, at least when I started working in this, not many people from engineering, at least my background is mechanical engineering, not many people in mechanical engineering used to work on the field deployment. People used to work on medical related technologies. Classically, many engineers have been working on it, physicists have been working on it, chemists have been working on it. There is no such, it's not that it's new. But at that point of time, now I realize that what mistake I made, but I think that it is important to discuss. My idea was very simple, that in the lab, let us develop this technology well, and we could get success in getting publications, patents, etc. out of that. And then when people approached us that well in the lab it is working, now it should be commercialized, this and that. So then make a plan of from the lab how can we take it to commercialization. And that makes it fail. Why it makes it fail? Because in the lab, the way in which it was designed with certain conditions which we do not keep in mind, but they are very critical. Like in the lab you just get continuous power supply. That we call as good quality power. If you go to the rural field, you will get power. It's not that nowadays there is no power, but uncertain, interrupted. In some places, power source may not be available. Lab environment. We talk about lab environment. Some labs are much more sophisticated than the other. But the basic lab environment it has a control. You will not have a lab with zero control. Whereas when you go to the field, it is absolutely uncontrolled. You have heat, dirt, dust, humidity, whatever is there, it is there. And you cannot do anything on that. If you are doing a diagnostic test with reagents, and several of the diagnostic tests with body fluids will require reagents. So in those reagents, typically say biochemistry based tests, you will require reagents. So those reagents, they need to be stored under certain conditions, transported under certain conditions. When you have a lab, the lab has an established system for that. Starting from a, say, 4-degree freeze to even -20, -80, depending on what you are storing. And we take it as obvious. The supply of these materials also, there is an established supply chain in every lab. We know what the suppliers and they supply continuously. So all these systems are completely broken in those places. You may have a central refrigerator somewhere and you can store up to a time, after that will degrade. All these things happen. The skill sets of people available there. Sometimes I, in a loose mood, tell to some of our colleagues that some of the colleagues have a complaint that our students, they are all useless, they cannot do things and that. But when you go to these people, they are at a level of education and all, who have to really implement on the field, with respect to that, all our students are Einsteins and Mahalanobis. So, absolutely no comparison in terms of their relative education. But those people are very sharp and brilliant and intelligent. You have to empower them. But that's not easy. Unless you, empower them, they are not able to do that. So that is difficult. So, and there are ways where technology can beat all this. So you can have, you say, I do not care what all this. I will have a small automated, highly automated instrument, which will run on its own, have a cartridge. Every test, you just discard the cartridge. So I do not care what it is, because the sophistication of the technology is very complex also. That is taken care of. Just like this TrueNAT, CPNAT type of technology. There are so many such. And the Western world actually means that as point of care diagnostics. In the Indian perspective, that will not work in a sustainable manner because of the prohibitive cost and complexity. So our focus cannot be such a thing which is very nice and technology-wise brilliant, automated, but people cannot pay for it. So we have to find out something where it is simple, user-friendly, can be used anywhere, but not with much compromise on the accuracy. And this is the greatest challenge that the developing world diagnostics requirement gives. And this is where the opportunity is there for Indian researchers, from the Indian context. I am telling this to you because with my experience what I have realized is that we actually never identify the correct problem which will set us in the forefront of the context. We are always seeing someone from MIT, Stanford, etc. in a big journal publishing something and doing a bit of tweak on that and have the next publication somewhere, which is also very important. But it is not according to our need. So if we do it according to our need, that need may not be the same as what our MIT, Stanford people they are doing. More than just about 10 years back, I was visiting UC Berkeley, and I found there is a center with which we had a collaboration at that time, Center for Emerging and Neglected Diseases. I do not know whether that center exists still now in UC Berkeley, but similar centers exist in many big universities. So for them, what is emerging and neglected diseases is for us a daily disease. So they are having special people to actually work on that. Whereas our common theme is that. So we have a greater chance to work with the real samples, real conditions, and therefore that is where actually our research can get focused. And we have to set it up correctly. So how can we overcome those limitations? I will give you some examples of how we move forward. So we first started with the point of care testing of fingerprint blood. So if you just give the brief image and the video will run, then it will be easy to explain. So you can see this black box, which is basically a controlled environment inside which you have optics and electronics in a way that you can create a controlled illumination setting for a camera, standard camera to take an image. So why that is important? Now if you look into this, you have a paper strip, and in that paper strip you take one drop of fingerprint blood, and let us say that blood is here. If you look into this, in fact this will take a long time for us to come to this stage from use of the pipette. So initially we were all doing with the use of pipette, and this is where I always give this insight to people who come from life science. People who come from life science, despite their talent, your mind is set to the lab, and that is the biggest challenge in getting a real life project. So when you are having such a real life system, in rare cases we can expect that there will be a technician who will be sitting with a pipette to actually collect and handle the fluid. So you basically are bringing your finger, after your finger is pricked with a lancet, to that spot where by the capillary suction the paper will suck. I will tell you a few small design things which people will not think. So now what you are going to do, two things. One is, let us say you are trying to measure the plasma glucose, which is the common sugar test. In the glucometer, the point of care technologies which are common in the market, what people do is people make the whole blood glucose by a electrochemical principle, and then use a correlation to convert the whole blood into the plasma reference. That correlation in many cases works, or most cases works, but in some cases it deviates. So direct plasma is always good, and these are colorimetric tests where direct plasma is essential because deep red color of the red blood cell interferes with the colorimetric analysis. So you have to separate the RBCs. So what we have is a small membrane filter here, which will filter out the RBCs and the plasma, which is separated. Now there is a small channel here between these two circles. That channel is a micro channel, so that once that plasma is there, by capillary action it will move from the source to a destination where the reagents are there. There are two ways in which you can put the reagent in that reaction circular box. One is that you can do it instantly when the test is being done, or you can have it lyophilized. That means it is actually there in a dried form integrated with the strip, and once the liquid comes, it's just like the childhood suspension medicine of the antibiotic that young kids take. So when the suspension comes, then that it becomes an active reagent. So then with that plasma will react with the reagent and the color change is there. So typically we always keep a kind of, you can say, acid-base reaction at the end, which will produce certain typical observable color change. So let us say that we have the standard glucose oxidase peroxidase reaction for the glucose analysis, and then we have a side reaction which will produce, say, a discernible color, in this case reddish brown color, and the deeper the reddish brown color, more the sugar. But we have to imagine this is where we have to be quantitatively accurate. So it is not like our school chemistry where the pH, this red litmus and blue litmus, or maybe a pH paper qualitatively tells the color. That kind of qualitative subjectivity is good for just a color scale, but it is not good for a decision to be taken out of quantitative characteristics. So whatever color is that you get of that image using say field camera here, and how do you do it? You insert that paper strip into this, just like a credit card inserted into a credit card area. Then you take the image, and after the image is taken, you have a smartphone app, and that app basically has an algorithm which connects the image features, which will extract. One simple extraction is just RGB value or a combination of that. But actually you can deep dive into lots of other different types of features, and then with a machine learning algorithm you can figure out that which are most important features and correlate that feature with some training cases where the samples value that you get from, say, an automated biochemistry analyzer from the lab that you know. So in that way you develop a correlation, but it is not a mathematical Y versus X correlation, which is a feature mapping from, say, one image set to the value, the digital value. So once you have the data and that you can display in the smartphone. So simple one, but it requires a lot of technological aspects like image analysis and all those things. And as I am telling that these things are not rocket science. These people used to know even several years back. But why these have not really got into a viable technology in the way in which currently it is going? One of the reasons is that the image analysis and AI application was not that powerful when these concepts were first introduced in the market. So there would be a lot of accuracy gap, which currently using the dynamic machine learning, one is able to overcome to a large extent. But I will just go through a few things which will tell us that every technology that you develop, we have to keep in mind, a technology being developed is almost like a baby conceived, and we all love our own children. So very difficult for us to have a neutral judgment on what is good about it and what is not so good about it. So one of the things which remains a bit of time taking is that when the plasma is going from one end of the stream to another, it is going by pure capillary action, which is a wicking action. It is just by diffusive movement, and therefore it takes its own time. If you want to make it fast, one of the possibilities is to apply electric field, because you already have a surface charge in the paper by virtue of the carboxylic acid group, which has a negative charge. So you can drive the blood flow, which will have more abundant positive charge, say, in the sample to make it overall neutral. So by electric field you can make it move, which is known as electroosmosis. But to make an electric field work on a stream, you require electrodes. And electrode deposition is something which, all these things, they require manufacturing or fabrication. So electrode deposition classically in the MEMS technology has always been considered to be a sophisticated process. Now, that sophistication is okay if you have a large scale scalable fab, but if you do not have that, then you are not able to do it. So this is about 15 years back. We were working on this and I told to some of my students that why don't you try with this in the paper strip, just make a pencil sketch, HB pencil sketch, this black things. So with the pencil has lead in the tip and it has graphite. So the intuition is that when you sketch on it, it will actually have graphite deposition and that can act as an electrode. Now it may appear to be a bit crazy and funny, and it was difficult for me to convince the students to actually do the experiments that they should do. But once it was done and we just connected the copper wire leads and all, we found that significant improvement in the rate at which the displacement of the fluid as a function of time, and that is taking place. So then maybe not as a design, but that is how he invented the technology paper and pencil microfluidics. And now when we see, this was a paper in a lab on 2012, long on that. And now when I see that large number of research groups in the world work on this technology, at least it gives a satisfaction that this is not a MIT or Stanford technology we borrowed and tried to. Very simple, but at least it is emerged from our IIT microfluidics. Now, but again, some people might think that are we talking about a cottage industry that people will seek and make pencil sketch and make products? Not like that. This is the in principle thing. So we have later on automated with the graphite deposition, automated technology. The principle which is given, and in fact school children can actually work on these toy type of things. Now coming to one after the other certain things where it's not that the challenge is always solved. So if you think about that in a good life science or a bioanalytics lab, you will require a good microscope and sometimes a good camera, but almost all the time a good microscope, because you need magnification. Now I will tell you that where such lack of such facility can give a challenge. So this is a project, in fact it is still ongoing project. So this is a lateral flow strip, which is just like a COVID rapid antigen kit. So these are very commonly used for antigen antibody tests. So antigen antibody tests are on such a collage of membranes, which are called as lateral flow assays, are simplified versions of the ELISA-based tests which are often taking place in the lab. So once you do that, what you actually want to do? So there is a protein which is an antigen. So you want to use that as a biomarker and you want to detect it. The challenge is that all these lateral flow strips are typically having very low sensitivity. That means that beyond the threshold concentration only it is possible to detect, otherwise it is missed. So how can we detect it when the concentration is of trace amount? Why it is important? Because there are many protein biomarkers which are common inflammatory biomarkers, and there are many tests which are not cancer diagnostics per se, but they can be used significantly for screening purposes, like CA125, prostate specific antigen, and this we are doing on breast cancer biomarker. Now, when you are trying to do that, what biomarker it is not that important for a technology. What is important is how we can detect the trace amount, low concentration. So you need a very specific binding that you want to catch. So what we did is, so first of all, general principle I am sure all of you know because you are in a focus group, but I am just telling for the sake of generality, that if you have an antigen, you want to interrogate whether that antigen, which is an antigen disease specific, whether that is present or not. So as a biosensing principle, you will have antibody which will bind with that antigen. That antibody is sitting somewhere on that kit. So if that antigen is coming by capillary flow, by surface tension, then that antigen will bind with this antibody. And then something what is formed is called as antigen-antibody complex. Now by capillary action, this antigen-antibody complex will move, and at some location there is a secondary antibody. And this antigen-antibody complex, that antigen part will bind with the secondary antibody, and if it binds successfully, in such a lateral flow strip you get a test line. There is another one where you have a reference antibody where even if that antigen is not there, you will have non-specific binding and you will see a control which shows that the capillary action is working. So only if the control line is working, it's okay that the strip is working but it is negative. But when both the test and control lines are there by surface plasmon resonance, then it is positive. But that surface plasmon resonance is a technology which will not be able to detect that very low concentration because of the lack of resolution. So what we have done here is that we tag these antibodies with carbon dots. So when the antigen-antibody complex is moving, that carbon dot tagging is there. Then if you shine ultraviolet light on that if you have a particular emission, then when that particular light falls on this, then depending on the specific binding, that antigen that you wanted to detect, if that binding is there, it will have its emission spectra accordingly. It could be one particular very precise color which colorimetrically is difficult to detect, but in fluorometer we will be able to detect that fluorescent signal because its wavelength is very much fixed and precise. But the question is who will sort of, then again you have to bring it to a lab where the big spectrometric analysis is there. Who will do it on spot? So on spot if you want to do it, first of all you have to magnify. So you require a microscope. And once you require a microscope and you do not have a lab, so what you do, so we make this 3D printed microscope by basically combining objective, eyepiece, lens, all those things together and integrating in a small platform. And it is about say total 1500 rupees around cost, taking the 3D printing charge. And this can give easily 1000x magnification. So once you have the magnification, but that still is not good enough because you do not have the fluidimeter. So what we are doing here is simply we are putting the smartphone and taking an image of it. So then that is where AI comes. So we are training the algorithm with whatever was the concentration that gave rise to this one. So create a mapping. So that for an unknown case, when that image comes, with that AI the feature extraction is made and you can predict the low concentration. So in this way something which is highly resourced, and in fact a highly resourced version of this also is not available in the labs. And so that this gives an example how the physical technology and AI combined can actually give a very meaningful solution. Now bringing a bit of focus to the infectious diseases, and one example that I gave that can be applied to infectious diseases like antigen antibody, but that will be mostly in the periphery of say a virus. But if you want to really test a virus in terms of its fundamental signature, the nucleic acid. So nucleic acid tests are problematic simply because they require more resources. So if you are doing with say RNA virus, so you require first a reverse transcription from RNA to DNA. So for that a procedure has to be there. So in fact even the prior of that you need a RNA extraction. So you need a kit for RNA extraction. Then RNA to DNA, reverse transcription, and then the DNA amplification. And for that typically you have a PCR, which is the cyclic heating, cooling. Every cycle it gets amplified in a geometric progression. And when you have significantly large number of such DNAs, possibly that particular gene sequence which you are targeting, that can be captured again with a fluorescence signal, which a PCR does. Now when the COVID period came and we understood that it is not so easy to have such a focus everywhere in resource limited settings. And when the COVID, even the first wave first came, people in the media were always talking about RT-PCR kit. And one thing that I was thinking in this way, that you have the RT-PCR kit, so what? But if you do not have the RT-PCR machine and its use scalable, then only kit what it will do. And having such a scalable democratized use of RT-PCR machine is not there. But because the world of these particular activities mostly with the people who make these reagents, kits reach, etc. So that came in the focus. And then we thought that can we make a simplified machine? So we could run that, just click on that top right. So what we did is we made a small machine which what it could do is that instead of the cyclic heating and cooling, it could use the technology at constant temperatures, but different piecewise constant temperatures, which will guide all the way from the RNA isolation, you cannot say extraction per se, with the heat activation, and then use a master mix which will include the reverse transcriptase for RNA to DNA, and then primer, probe, etc. and all together in a way that when you put it in the machine, it will be an automated time-stamped procedure that when you heat it at about 65 degrees centigrade for 30 to 35 minutes, which is a common lamp reaction protocol, and then you will see that there is a colorimetric signal change. You do not open the tubes. This is very important because these are nucleic acid-based reactions, and the lamp reaction actually produces large number of amplicons at a very short time. So if you expose those to the environment, it will create carryover contacts. So you do not actually open those tubes and just take those tubes out of the machine, put it in a side slot and take the smartphone picture of that and do the analysis. We tried to also do a few more things to actually democratize it in a different way. I mean, I do not have time maybe to talk about that, but this is a topic that nobody touches. So, sample collection in such things. All of you have seen the rapid antigen test, but the rapid antigen test also requires the due diligence sample collection, be it nasal swab, oral swab, oropharyngeal, nasopharyngeal, whatever. Even the most trained technicians falter in collecting the sample in the right way, and these kits are made for self-testing, and nobody would be actually doing it due diligence. So the basic premise of this test is flawed. You are talking about sensitivity, specificity, etc. It depends a lot on the sample collection. So a huge effort should go in a way that if the sample collection is flawed or simplified like a saline gargle test, that you just run the bottom one, which we have been working with ICMR, RMRC in Bhubaneswar. So this is like for children, and we found that very difficult to poke the nose and all the things. So you can just give them a saline solution for gargling, and it will be not as concentrated as the real Prof. So what adjustment that you can do to make a good now. So in this way, although COVID is gone, but seasonal flu is very important in the schools. And when one child gets affected, the entire class gets affected. So if we can have simple screening tests, it can help a lot. And but now you see as I was telling initially, that every test what you develop, we try to critically understand that what are the gaps. So this black box based test, in a way it is much better than having to have your vein puncture and taking a sample to the lab and do the test. But let us say we are working with the sugar test, hemoglobin test, very important for common people, public health. Now let us say someone, a diabetes patient, who is using a glucometer for daily monitoring because for insulin dosage it is required. More than the cost is one part, it is also inconvenience. There are many people who are apparently quite healthy and all, but they suffer from this lifestyle disease. Someone is having to go to the railway station, airport, community center, taking part in a meeting. Now in that time it is not possible, suddenly you bring out that box and do the test. So we wanted to see that if you say eliminate that box, what will happen? The challenge is that we started with what? That we want a lab control in a lab test. Now when lab control is not there, you impose the lab control in that small box to whatever extent possible. But if that box is gone, your complete control is gone. And if you are doing it with only your mobile phone camera, every mobile has a different camera setting. and the background lighting also can be arbitrary, and the human who is taking the image also can do it arbitrary. So you cannot really set up a standardized reference calibration, which is very much required to set up the method, and therefore it can go absolutely random. And what we wanted to do, actually, we wanted to standardize it. At that point of time, startup company SPARC Technology from Pune, they came and they joined with us. They wanted to take this technology and also to implement it for commercialization, and they incubated with us at IIT. So we developed certain algorithms which have a combination of physics-based, the optics analysis with AI and relative consideration of images. I can tell you in a very simple way that let us say you are having one spot on the paper strip which you are imaging. So when you take it in an absolute sense, of course it depends, it varies. But you take another reference spot, and with respect to that, if you analyze that relative thing, will have many things nullified. And lot of things of light matter interaction which come from the physics of optics. So nobody in diagnostics actually look into that. So if you put all those things into your method, then actually we try to see that without a device it works to a great extent, and because it is AI driven, more and more training data you get from the diversity of humans, you will always get the next time more accurate things. So we work with two technologies. One is HemoQR, you can run the top one.
HemoQR
is a hemoglobin test.
HemoQR presents an effective solution for hemoglobin detection through its paper strip-based microfluidic reagent. This cutting-edge product combines advanced microfluidic technology with calorimetric analysis for accurate and convenient hemoglobin level assessment. The paper strip is embedded with specialized reagents that trigger color changes in response to hemoglobin presence. Leveraging the capabilities of a smartphone camera, the accompanying app interprets the colorimetric changes on the strip, translating them into quantitative results. This seamless integration of paper-based microfluidics and digital analysis delivers a user-friendly, on-the-go solution for hemoglobin level quantification. HemoQR's versatility makes it valuable for both medical professionals and individuals, enabling quick and reliable hemoglobin measurements. With its portable and efficient design, HemoQR simplifies hemoglobin detection, enhancing healthcare accessibility, diagnostics, and screening. To perform the test, prick the finger using a lancet. Use fresh lancet every time while performing the test. Depending on how deep the lancet goes into your skin, you can set it according to the rotator or in the lancet device. For thin skin, set the rotator at 1 to 2, and for normal skin, set it to 3 to 4. Hold the drop of blood against the strip's edge. Touch the hemo strip on the drop of blood. Scan the strip using the HemoQR mobile application. Get your hemoglobin results within a minute in the mobile application.
So this is as simple as this. You can keep all those things in your pocket and move, and anytime you want to do. The one that is below it, you can run, and then I will explain. So this is, I would say that perhaps the most significant thing that we have done. It looks very simple, but it empowers women monitor their reproductive system health at their complete privacy. So you can have a safe collection of the vaginal swab, and by a guided video, you can just do the test by putting it on such a strip, take the photograph, and it will give a 1 decimal accurate vaginal swab test. With that and symptoms combined, there are many interpretations which come which can talk about early screening of many of the such important ailments, and very important where there are places where there is no gynecology. And you can just do it on your own. We are trying to see as much as this is used by even adolescent girls in high school and so on, so that many of the things for which there are no doctors and people should not depend on walks and other people can disturb their things. They will do their own. The result result will come in the mobile and they can then
This is
forward it
useful
to the
for
doctor who
individuals
they can
as well
consult.
as professional
And
use.
then the result can come. So let us go to the next slide. Now, as I told you, we have come almost towards the end of this presentation. So when we come to a diagnostic test, this is the ultimate question. So what we try to do, try to simplify, and further simplification is also there. That I have not shown that is completely non-invasive, just spectral analysis based, just like a pulse oximetry test. Now that kept on one side, that is technology. But as a patient, what we want? Say, my way of having an intervention, because I am not a doctor, so my viewpoint is mostly like a patient's viewpoint. That if I go to a doctor for something what I want that the doctor will detect what is my problem and treat accordingly. Very simple. And for that, I am having the liberty to tell anything. And this actually happens. A good doctor is a very, very, what I would say, wise doctor. Will look into many things and come to a interpretation about what has happened to you. We have all heard about the legendary Dr. Bidhan Chandra Roy. We have not seen him, but some of my uncle and all, they have been a student at that time, medical college, and they say that Dr. Roy, when a patient enters the chamber, Dr. Roy will look at the patient and then will be able to make certain inferences. Sometimes when this becomes a skill, it also becomes a myth. May not be to that extent, but definitely he had a special intuition. And how this intuition is developed is something like this. A good doctor will actually try to diagnose things holistically. So when you are entering the doctor's chamber, the doctor's analysis starts from that. Whether your face is looking pale, in what way you are talking, in what way you are walking, even sitting there, basic physical clinical examination. And I can remember that when we were young children, we used to go to someone who is a family pediatrician, the so-called child specialist of the children of the family. And that person would know us from the very beginning. I cannot remember even maybe one or two occasions possibly, yes, that doctor who used to treat me in my childhood ever proposed a diagnosis. But I was having many diseases in my childhood. Not that I was free of that. But I am living now, standing here and talking, so all those diseases got rectified. So how did this person do? If you are speaking with a good doctor, you will see that the doctors, maybe not in a very conscious way, they go for a method of elimination. So you go to a doctor and tell, the doctor will ask you that what is your problem. You say that I have headache. Now doctor knows that this headache could be because of 1000 reasons, possibly starting from simple migraine to brain cancer. But doctor is not Dr. Google. So if you give this to a Google search or maybe ChatGPT, you will at the beginning see a fear of possibly you could have cancer. And then all the links of Anderson Cancer Center, this, that will come, Mayo Clinic and all, it will make your entire mind so much disturbed that not cancer but you could have heart attack. So that kind of practice of medicine is now what AI is sort of promoting to do. Now doctors do not do that. So what doctors do is that they go by an intuitive elimination. So doctor will converse with you, will look into the past medical history, make some physical examination by himself or herself. By that, already a good doctor from those 1000 would come down to 5. And then maybe when it comes down to 2-3, doctor is not able to close that dilemma, and because technology is available, doctor will go for the specific diagnostic test. So a bad doctor will go for any number of diagnostic tests. A good doctor will go for only that, which will give a decisive conclusion. So that means that there is a difference between diagnosis and diagnostic tests. In the modern technology-driven world, somehow they are becoming synonymous, which is absolutely wrong thing. So as a patient, I would tell a doctor, a great doctor, who with zero diagnostic test to diagnose what is happening in a reasonably accurate way, at least screening wise. if not the final decisive. So for that, you require some analytics of the pre-diagnostic test part and combine that with the diagnostic test, and that will actually give a better diagnostic accuracy. So this is something. So we developed a method of oral cancer and pre-cancer screening. So if you could click this, possibly it will be done. So it started again around 10 years back. We were working on this technology, and so this is actually a thermal camera integrated handheld torch system. So what it does is that it takes a thermal image around the lesion and it converts the thermal image to a blood perfusion image by a proprietary algorithm developed by us. Blood perfusion image data can actually tell you quite accurately about the local vascularity. And we all know that because cancer progression at some point of time may require and may involve angiogenesis and all, change in vascularity or very dramatic alteration in vascularity pattern at certain place can indicate something suspicious. But it could also be due to many other factors. So you have to look into it holistically and come up with a recommendation and not just depend on that data. So at that time we did a what I would say a stage 1 clinical trial with Guru Nanak Institute of Dental Sciences and Research, and it could resolve many ambiguities. Where even trained doctors, while looking into the lesions, they found that it's very difficult to demarcate between some typical fungal infection with some of these, or maybe standard features inside the mouth. So they are very standard for some people with something which is abnormal. So then what we realized that after this technology came up and sometimes good publications are important because it gives a important spread of the technology. So when this was published in the PNAS, then people got more interested to learn about it, and then many doctors approached us and said that they wanted this kind of technology. Then we realized for overall oral screening, because oral cancer, pre-cancer is a small part of the overall this oral and dentistry big community. So then what we realized is that we could create an app where starting from the patient data, history, and some even there are some features are inside the mouth. Simple photo can be taken and it can be compared with some reference things. So this is without any diagnostic test. And say tobacco consumption, habit, this kind of inputs. So it will give a AI-driven first layer of screening. Then if there is a red flag, then we can use this technology. So what we have done is we have also tried to integrate this with the intraoral camera, which typically the oral practitioners commonly use. And so integrate the intraoral and the thermal camera together so that we can get a multimodal analysis. And currently the device is like this. We are trying to modify it every stage, and the technology backbone remains the same. But the important message is that if you do it only by this technology, there is a chance that it gives absolutely wrong prediction. But when you are going by this layer by layer screening with patient input, history, some images, and then are getting down to this, there is a greater chance that you screen it correctly and get into the right direction. So a combination of AI and physical technology, which can be applied at resource limited settings. And I will not run through the videos, maybe you can understand one of them. So what we try to do is we try to, this one is a pre-COVID era when some of our technologies were getting standardized. So many of such camps that we participated in, every such thing gave us a lot of learning. And the learning is very important, that the greatest fools are those who develop technology in the lab in the classical scientist way and think that it will work on the field. So that mindset has to be somehow changed. And if you bring in that design aspect from the very beginning of your lab work, you have a greater chance of succeeding. This I learned out of initial mistake and experience, but possibly now when people are working in these areas, they can use it for more purposes. So what these technologies do, beyond serving for good health for the community, they can also empower the community, like women. And we have seen many women actually forming enterprises and making their own livelihood out of such things. So in a way, it solves the holistic problem of people not having enough jobs, but they can find this as a sustainable ecosystem. And this ecosystem has a different business model. When you go to a 100 rupee diagnostic test, 30 rupees kept for the so-called commission of a doctor. If you go to any diagnostic center, they will ask you what is the name of doctor. Actually, it is not required. Many tests. So if you ask them that why you require this, they say that we have an assigned, if the person is getting correctly, assigned finance associated with that, whatever way they do. So when you come to a 1 rupee test, it is 30 paisa or 2 rupees 60 paisa. So 60 paisa will not excite a doctor. So doctors are the first set of people who will oppose this test. So what is the standard reference of opposing this test? This cannot be accurate. Who are the culprits of why this cannot be accurate? Is over advertisement of that AI can do everything. All AI based things are there, many of these are, they give absolutely random results. Nice smartwatch technology, but no good in the clinical results. But if we combine AI with that clinical results, it actually becomes very useful. And it may be 30 paisa for one person or 60 paisa for one person, but in a lab, say per day 100 such samples were there, so 100 into 30 rupees for a say 100 rupee test. And in such a place where nothing is available, that 100% will become easily 1 lakh person. And then 60 paisa for each of these 1 lakh is not a small amount. So this microeconomics is an entirely different volume altogether. I wish there is a good economist who works on this. I trust many people, but I do not have the knowledge to do all this. But it all shows that this is all a holistic ecosystem based thing, and you have to think these technologies used
Professor Chakroborty
in a completely different way as compared to what we think traditionally. So with this, I would like to close this talk. Thank you very much for your attention. I have tried to put some names here of the faculty members who have contributed, students who have contributed, etc. Some I kind of unwillingly I will miss, but it's a whole team effort. It's not an individual's work, and of course, large number of funding agencies have been done. Thank you very much.